session is going to start in some few minutes. Okay, and just wait for a minute. So just our expert will going to join in some minutes, and as well as the head of department. Okay,
Yes.
and your friends if you want to join, so that you can get the benefit from this the presentation.
Power off.
हाँ सर, स्टार्ट होने वाला है। हाँ सर, वो प्रेजेंटेशन था ना। ओके ओके ओके।
Hello.
Saurabh,
Hello.
please mute your mic. Do you want to say
OP, you can
something?
start now.
Okay, sir. Sir,
OP, you can
external
start.
is external does not join. External.
They
Sir,
have joined.
no, not join. I am going to call him. I'm going to call him, sir.
Okay, okay, okay.
Welcome, sir. Welcome, Professor Vijender, on the MTech Dissertation Bio West. Are you audible, sir? Professor Vijender, are you audible? Yes, sir. Your voice is coming.
Hello.
Yes, sir. Voice is audible.
Hello.
Yes, sir. Hello. Hello. Yes, sir. Hello. Professor Vijender, you are audible.
Just for
Am I audible? Am I audible, sir?
Yes. Good afternoon.
Okay.
Good
Good
afternoon.
afternoon, sir.
Now it's okay because I was not hearing the voice.
Okay. Shall we start?
Yes, immediately we can start.
Okay. So a very good afternoon to all the students and and HOD sir and Professor Vijender. Uh, I Dr. O.P. Verma, the supervisor of Drishti Yadav. I welcome you all in the MTech Research of West on the metallistic driven energy optimization of multi-FET operator. So Drishti, before going to the presentation via West, I want to introduce our external examiner, Professor Vijender Singh received his BTech in Electrical Engineering from JV Pant University of Agriculture and Technology, Pantnagar in Uttarakhand, 1995. He received ME degree in Electrical Engineering 2000 and PhD in Electrical Engineering 2007 from IIT Roorkee. He has published many papers in these international journals and conferences, including the book chapters. He has chaired many international conferences. More than 25 MTech theses have been completed under his guidance. At present, he has six PhD students under supervision, and he has and 10 PhD are completed. He is working as a professor in the Instrumentation and Control Engineering Division at Netaji Subhas University of Technology (NSUT), New Delhi. His area of his area of research including process control, biomedical instrumentation, artificial intelligence, and image processing. So thank you, sir, for accepting our invitation. So now I directing to the Drishti. Please start your presentation. Okay.
Thank you.
You start,
Uh,
please.
Thank you, sir. First of all, very good evening to one and all. Respected director, sir, team of Department of Instrumentation and Control Engineering, external examiner.
Drishti, your voice is, I think, na some noise, some cutting is there, है ना?
Okay, sir, let me just check once.
Please proceed. Please proceed.
Sir, is it audible now? Hello? Am I audible?
Not
दृष्टि
very
ये
well.
थोड़ा सा ना ब्रेक हो रही है थोड़ी सी बीच में आवाज आपकी
हाँ
एंड
थोड़ी सी
ये जो है ना आपका जो एक माइक है वो ऑफ आ रहा है
हाँ वो सर प्रेजेंटेशन वाला होगा इसलिए उसका
प्रेजेंटेशन
ऑफ आ
वाला
रहा है.
ओके ओके
Yes,
हाँ
ठीक ठीक
दृष्टि हाँ बोलो.
ओके गोइंग ऑन नो प्रॉब्लम
sir. Oh, audible.
Some network issues there, I think.
हाँ
Sir,
देयर आर सम
let me just change my.
दृष्टि फिर एक काम करो आप अपना वीडियो ऑफ कर लो देन आई
वीडियो
थिंक
ऑफ
इट
कर
विल बी
लो.
बेटर ठीक है
हाँ वीडियो ऑफ कर
Okay,
लो. हाँ.
आप अपना वीडियो ऑफ करो देन ओनली इट विल बी वर्किंग थोड़ा
okay, sir.
बैंडविड्थ में प्रॉब्लम हो जाती है
हाइड बेटा हाइड.
Yes,
हाँ.
just.
इसको हाइड
Am I
कर
audible now?
ओके
बेटर.
जस्ट स्टार्ट स्टार्ट नो
Is
प्रॉब्लम
it audible?
हाँ
हाँ
नाउ
नाउ
इट इज
नाउ
ऑडिबल
Now it is
Now
okay.
it is okay, I think.
Yes. Thank you, sir,
वो थोड़ा
for
प्रॉब्लम
suggestion.
हो जाती है, वीडियो में ज्यादा
हाँ,
बैंडविड्थ लगती है ना.
चलो चलो
Please
स्टार्ट करो. हाँ.
go ahead.
So I once again welcome everyone to my discussion presentation entitled Meta Heuristic Driven Energy Optimization of Multiple Effect Evaporators. So first of all, let me just the execute summary of my dissertation work. The dissertation has the solution of non-linear steady-state energy model of multiple effect evaporators, that is MEE, along with various energy saving strategies using meta-heuristic techniques. The dissertation also achieved the screening of best operating scheme of multiple effect evaporators, ensuring highest energy efficiency. The dissertation also achieved the solution of dynamic energy model of multiple effect evaporators using meta-heuristic techniques to understand the transient behavior of this system. Also, the dissertation was able to make significant research contributions in reputed journals, international conferences, and book chapters. So, whatever I will be discussing today, this work has been published in the chapter Research Article, Neural Computing and Applications, and a research paper in elsewhere. Today, my discussion will be focusing on these points: the introduction, systems, research objectives, methodology, results, and the concluding remarks.
विजेंद्र सर
What
ठीक है, मतलब आवाज की
It's
कुछ.
okay, it's okay, it's
ओके.
understandable, no problem.
चलो.
Go.
ओके सर, ठीक.
so, so shall I continue?
Yes, yes, continue.
Okay. So, what is the motivation behind choosing such a topic? Usually, we see that the distributed energy scenario focuses on the utilization of renewable sources of energy and dictates transfers from non-renewable sources to renewable sources. As such, biofuels are gaining attention across the globe for utilization in transport applications to ensure sustainable development. In such scenario, black liquor is a waste residue obtained from the paper and pulp industries corroborates to a significant source of biomass, which can be converted to a biofuel. It is estimated that approximately 170 million tons of black liquor is produced per year, which possesses of about 2 exajoules of energy. So it is a very high amount of energy. So the prime motivation of this work is conversion of black liquor to biofuel. Now, here we can see that black liquor has been used to produce transport fuels such as hydrogen, methane, methanol, and DME, which have high calorific values compared to the standard petrol and diesel fuels. Thus, this tabular representation corroborates the significance of black liquor as its transport application. Now, before using black liquor as a biofuel, it needs to be evaporated to significant concentration using a multiple effect evaporator system. Now, this concentration increased from about 12 to 14%, that is the concentration when black liquor is drawn from the digester, to about 55% of solid content. This concentration is achieved by using the multiple effect evaporator, that is the MEE. Also, the MEE is extremely energy intensive unit, and it has been reported that it contributes to about 50% of the total energy consumption. So, in all, the prime objective or the prime issue is the energy optimization of multiple effect evaporators. Now, what is the problem statement? The first thing is the energy optimization of multiple effect evaporator, but secondly, another important objective is the assurance of a good product quality to ensure that the black liquor is used as a biofuel in a good manner. So to achieve these objectives, the need is to ensure to perform exhaust calculation and modeling of the steady state and dynamic behavior of the ME. The steady state parameters will give us the optimal process variables, and we can also integrate various energy saving strategies to ensure the optimum energy efficient performance of the MEE. Now, the dynamic model will help in understanding the open loop dynamics of the system and understand the variation of the process parameters with respect to time. This dynamic model is obtained by using the steady state process parameters, such that for the steady state dynamic modeling helps in the design of controllers, which in turn is useful in uh, undertaking these two objectives, that is design optimization and assurance of a good product quality. Based on the literature review, I have seen that various works have been proposed in the field of mathematical modeling. Also, various solution techniques have been used, including the iterative methods, such as Newton-Raphson method, then Gauss elimination, Gaussian method, then IPM, interior point method based on the dynamic programming, and evolutionary approach, a soft computing approach, genetic algorithm. Also, in the field of dynamic modeling, the evaluation of system transfer function has been done using the concept of linearization, space representation. Now, based on this literature review, what research gaps I have seen, the first thing, that is separating techniques and IPM methodology, are slightly computationally complex and are sometimes inefficient due to the dependency on the initial guess. So the thing is there any other solution method? So we have an answer, yes, that is the meta-heuristic techniques, the meta-heuristics, which are capable of solving complex computational problems. Now, here that G an evolutionary approach, which is also a meta-heuristic technique, has been utilized in solving the mathematical model of multiple effect evaporator. However, the convergence issues and the stability parameters are to be ensured to achieve proper convergence and optimal solutions of the system. Also, most other meta-heuristic techniques, including the also and uh, more independent techniques, have to be addressed. So, based on this, the first research gap I saw was the use of meta-heuristics for model solution. The second thing is the dynamic model has been limited to the evaluation of the system function only, and none of the research works that are published till now have focused on the solution of the dynamic model. So this is another research gap that I saw, the solution of dynamic model of ME. Now, based on this, research perspectives include the energy modeling of multiple effect evaporators in the steady and the dynamic state. Thereafter, the screen optimal parameters of steady state modeling using the meta-heuristic techniques. This will be the steady state model solution. The techniques employed are PSO, GA, that is genetic algorithm, D, differential evolution, water cycle algorithm, IC, imperial competitive algorithm, harmony search, colony optimization, and cuckoo search. Also, the steady-state model solution will yield the optimum steady-state parameters. Here, we will also focus on the screening of the best optimum scheme of multiple effect evaporators based on various energy saving strategies. Now, after this, the focus will be on the solution of dynamic model, including the simultaneous ordinary differential equations using a maiden attempt of Fourier series and meta-heuristic techniques. Now, this dynamic model solution, as I said, is achieved by utilizing the optimal steady-state parameters. Now, based on this, my presentation is organized in 5 chapters. The first one is the introduction, that is the motivation, literature review, and objectives, which I have already discussed. Second chapter focus on mathematical modeling of energy, which involves the dynamic model and steady state model and the multiple effect operators integrated with energy saving strategies. The third chapter models the formulation of objective function, the solution strategy, and different methodologic techniques. The fourth chapter will be the optimization results discussion of the steady state dynamic model solution, and the fifth chapter we will have the conclusions and future scope. So, as I said that I have already discussed chapter 1, I will be focusing now on chapter 2, that is mathematical modeling of ME. Now, let's see the multiple effect evaporator in the BS configuration, that is the backward feed flow configuration, and I have named it as number 1, that is the base model. Here you can see that the first let me introduce with the relations that we represent the state. T is the temperature, lambda is the latent heat of vaporization, capital H is the enthalpy, H is the enthalpy of the liquor. So here we see that the MEE has 7 effects arranged in such a manner that vapor generated in the first effect is fed as an input to the second effect, the vapor generated in the second effect is fed as an input to the third effect, and so on. Now, the liquor is F, it is shown here, is fed into the seventh effect, and subsequently, the flow of air is from the seventh effect to the first effect. The second model, here we have integrated energy saving strategies. Here the energy saving strategy is the steam split operation, that is the SS operation, which is integrated with BF model, that is model number 1. Here, steam, that is B, is fed, split into two fractions. The Y fraction is sent to first effect and minus Y fraction sent to the second effect, that the vapors generated in the first and second effect are added and sent as the vapor to the third effect, as an input to the third effect. In model 3 of the proposed system, we have the feed split operation, that is FS, in which the feed, that is the liquor, is split into two fractions, K fraction sent to the seventh effect and K fraction sent to the sixth effect. The third model, feed preheating operation, PH, here the liquor, which is to be fed to the seventh effect, initially is preheated using a preheater, and the preheater has input from the 1 minus m fraction of the vapor generated at the sixth effect and total fraction of the vapor generated at the eighth effect. Now, based on these models, other model configurations have been made, that is 5, 6, 7, and 8, are and combinations of the earlier models. Now, mathematical modeling, for this we some assumptions, and I have taken ideal condition. That is, there is no variation in the temperature loss effect. There is no loss of heat to the surrounding, and there exists thermal equilibrium between the liquor and the vapor. And I have not considered any real-time land complexity, including boil point elevation, falling, and scaling on the difference of the system. Also, what we require energy balance and mass balance at each effect of multiple effect evaporation. Also requires thermophysical correlations of the latent heat of vaporization, the vapor enthalpy, and liquid enthalpy. Here we see that these thermophysical parameters show a non-linear dependency on the temperature of the vapor generated. Now, coming to steady state modeling of model number 1, we first concentrate on the first effect. So here we see the energy balance equation. We see that we have two inputs and two outputs. One, the vapor entering first effect, steam entering the first effect, leaving the first effect, and the liquor entering the first effect and the liquor leaving the first effect. So accordingly, we will write energy balance equation and mathematically present as this. Also, we have another relation such that the latent heat supplied by the input steam is equal to the overall amount of heat transfer to the first effect. This is mathematically represented by this. Here, U is the overall heat transfer coefficient and A is the effective area of heat transfer. Similarly, for rest of the effects, that is from effect number 2 to 7, we will have other equations as well in a similar approach. In all, we see that we have 2 equations for each effect, and in totality, we have 14 equations for all the 7 effects. These equations we can represent using the symbol denoted here, that is F1 equals 0, F equals 0, up to F of 14 equals to 0. Now coming to, okay, now as I said that model 1 we have this here. Accordingly, the mathematical model can be developed for the rest of the models, including model number 2 to model number 7, that I will not be discussing right now. I will be focusing now on the dynamic modeling of model number 1. So coming to the dynamic modeling part, we have the mass balance equation at each effect of. Now we will formulate the total mass component balance which is utilized by using mass balance equation. Also, uh, the total mass component balance will yield us 7 first-order ordinary differential equations in which the dependent variable is x, that is the concentration of the black liquor. Now, focus on the total energy balance at each step of MEE. Accordingly, in using the mass balance equation, the final relation, that is dt1 by dt, here we can see that it is a first order ordinary differential equation in which the dependent variable is T, that is the temperature. So accordingly, we will have total 7 relations based on the total energy balance, and we have order ordinary differential equations in which the dependent variable is T, that is temperature. So in all, we have 14 first order ODEs, 7 in the dependent variable is concentration, and 7 in which the dependent variable is temperature. So these 14 first order ODEs are termed as simultaneous ODEs, that is the SOD. Now coming to the chapter 3 of my presentation work, that is the model solution of dynamic and steady state models. First of all, let me clear that I have used the MATLAB programming platform for simulation works. And these are the operating parameters of the MEE, which is taken from the North Indian paper mill at Saharanpur and some other published works based on multiple effect evaporators. Also, these are some other relations, other values which are used for simulation purpose. Now coming to the steady state model solution. First of all, let me introduce what are the energy efficiency parameters which are to be optimized. So there are the energy efficiency parameters or the performance parameters or the performance indices of the MEE. We have 2 performance indices. The first one is the steam consumption, that is the amount of fresh steam that is supplied to the MEE. It is denoted by V1 and its unit is in kg per second. The second performance index is the steam economy. It is the ratio of the total amount of vapor generated at each effect of the MEE to the amount of fresh steam supplied. And mathematically, it is represented as shown here. Here we can see that steam economy is a dimensionless and unitless quantity, and we see an inverse relationship between the steam economy and the steam consumption. Now to solve the steady state model, first of all, we have to formulate the objective function or the cost function or the merit function. So here we have set the objective function as Jz, which is represented as shown here. It is the summation of the square of the functions we obtained for the steady state model, which I denoted using f of 1, f of 2, and f of 14, like that. So we have 14 equations which are squared and summed together to obtain the objective function. Now my design variables or the decision variables are Z, and these are my design variables. 14 design variables we have. The first one is V1. We have the liquor flow rates and the temperature of effects as the other design variables. The other constraints include these, as denoted here. These are taken from the operating plant and published works. Now, these are the bounds of various temperatures and liquor flow rates, which are utilized for the simulation of various models, including the liquor flow rates also. Now, what is the methodology for obtaining the steam economy, optimum steam economy? The first step will be, we will be setting various parameters, including the heat transfer coefficient, the heat transfer area, the concentrations, and the bounds of decision variables Z. The second step will be optimizing the objective function using the meta-heuristic approaches, PSO, GAD, WCA, ICA, HS, CS, and ACO. And the third step will be computing the optimum steam economy based on the optimum steady state process parameters, including the thermophysical variables. Now we see that the optimum steam economy is evaluated using this relation as discussed earlier. Now coming to the dynamic model solution. For a dynamic model solution, I have used the Fourier series expansion as the base approximate function. This concept has never been utilized in the solution of dynamic models of MEE. So this is a maiden attempt from my side towards obtaining the dynamic solution of the MEE system. And the solution approach for solving SODs will be same as that utilized by Babey and Sadullah. Now, okay. As we saw that the dependent variables in the SODs are the concentrations and temperatures, so we will express the dependent parameters in the form of partial sum of the Fourier series coefficients with the center T naught. As we know as you all know the Fourier series expansion, so we will expand the concentration and temperature in this manner. Here, Xi and Ti are the exact analytical solutions, and Xi approx and Ti approx are the approximate solutions. Also, the coefficients of the Fourier series expansion, A0, Am, Bm, C0, Cm, and Dm, are the decision variables or the design variables which are need to be optimized. Here, L denotes the size of the solution interval, and Nt, the number of approximation terms in the Fourier series expansion. So, now coming to the objective function which is to be minimized for obtaining the dynamic solution is the weighted residual function, the WRF, which is an integral of the product of the weight function, which is taken as 1 for simplicity, and RT, that is the residual function, which is a function of time, the concentrations and temperatures, and the first derivatives of concentration and temperature. So we see that the Fourier series expansion for concentration and temperature, accordingly we will find the first derivatives as seen here. Now, what is the problem-solving methodology for dynamic model solution? So it is a step-by-step procedure. First of all, we have the SOD. We will develop the SODs for the dynamic model. Then we will select the number of approximation terms. Then we will formulate the constraints or the initial conditions. These initial conditions will be the optimum steady-state parameters which we obtain using the steady-state model solution. Then we will formulate the WRF, that is the weighted residual function. After that, we will call the meta-heuristic optimization algorithm. And for integral evaluation, I have utilized the trapezoidal method. And for handling the constraint violations, I have used the penalty function. So the penalty function is used to penalize the violation of constraints and is taken as the summation of absolute values of the constraint violation. Then we will display the optimum design variables, that is the best Fourier series coefficients, and accordingly we will plot the obtained approximate solution. Now coming to the chapter number 4, the optimization results and discussions. So first of all, I will be discussing the steady state model solution. So consider the model number 1, that is the backward heat flow configuration of the MEE system. Here I have compared the results obtained by various meta-heuristic approaches from PSO to ACO, and the steam economy and steam consumption have been highlighted here. So we see here that all the meta-heuristic approaches give approximately similar results, only the decimal or the fractional values are changing. Coming to other model solutions, here we see, here I have shown the results using the water cycle algorithm only, because all the models were giving similar results. So I have chosen here water cycle algorithm. In figure number A, we see the variation of steam economy with respect to the split fractions, that is Y, the steam split fraction, K, the feed split fraction, and M, that is the vapor split fraction. The model number 2, that is the steam split, the variation is shown here. Here we can see the maximum steam economy is obtained at a split fraction of 0.9. Accordingly, for model number 3, that is the feed split operation, the maximum steam economy is obtained at a split fraction of 0.9. And for model number 4, for preheating action, the maximum steam economy is obtained at a split fraction of 0.1. Now, seeing figure number B, I have the variation in steam economy with respect to the collective variations in M and K, that is the feed split fraction and the vapor split fraction. Here we see that the maximum steam economy is obtained at a split fraction K of 30% and M of 10%, and the maximum steam economy is 6.172. Coming to model number 6, that is BFF integrated with feed split and steam split operation, the maximum steam economy is obtained for a value of 6.89 at split fraction K of 50% and Y of 10%. Now, model number 7, that is the BFF configuration integrated with steam split and preheating action. The steam economy is maximum at split fraction M of 90% and Y of 10%, and the maximum value is 7.059. So here we see the graphical comparison of all the models, and we can see that model number 8, that is the backward feed flow configuration with steam split, feed split, and preheating action, give maximum steam economy among all the models of 7.092 at these split fractions. Now, this is a comparative summary of the present results compared with the published works and real-time plant steam economy. Here we see that model number 8 in the present work is a steam economy of 7.092, and compared to the real-time plant steam economy, we obtain an enhancement of approximately 50%. It is exactly 52.8%, but I am saying approximately 50%. However, I have to it is to be mentioned here that such a great enhancement in steam economy may be due to the exclusion of the real-time plant complexities, as I have not considered the boiling point elevation, then scaling and falling, which may have effect on the steam economy. Here is another graphical representation showing that the model number 8 in the present work with the steam split, feed split, and feed preheating action has the maximum steam economy. Now coming to the dynamic model solution. For NT, that is the number of approximation terms in the Fourier series expansion, that is taken as 3. This is the variation in liquor concentration. I have shown here the results obtained by PSO and HS, that is the particle swarm optimization and harmony search algorithm. Here we can say that approximately similar results we are obtaining, and these are the results for variation in vapor temperatures for NT equals to 3. Now, as we increase the number of approximation terms from NT equals to 3 to NT equals to 6, we see that an oscillatory behavior is observed in the variations of concentration at each effect. Similarly, on increasing the number of approximation terms to 9, more oscillations are observed. Also, it is to be noted that as we increase the number of approximation terms in the Fourier series coefficients, the constraint violations are decreasing, and there is significant improvement in the constraint violations or the deviation from the initial conditions. So, in the last chapter of my dissertation is the conclusions and future scope. So, it is concluded that the results validate the competence of these techniques in solving such complex simultaneous nonlinear algebraic equations and simultaneous ordinary differential equations of multiple effect evaporators. Then the results conclude that the best operating strategy is that of the multiple effect evaporator system in the BFF configuration integrated with feed split, steam split, and feed preheating energy saving strategies, which yields a steam economy of 7.092. Also, we have obtained the approximate solutions of SODs, which give the time variation of Xi and Ti. These approximate solutions are a way towards the controller design to achieve the objective of energy optimization and assurance of good product quality. Also, this work has explored the variation in the accuracy due to the number of approximation terms. The future scope include the inclusion of real-time plant complexities, the boiling point elevation, fouling, and scaling. These real-time plant complexities I have not focused in my work, so these are also good research work to be focused on. The second thing is the inclusion of other energy-saving strategies to further enhance the energy efficiency of the multiple effect evaporator system. These include the inclusion of TVC, that is the thermo vapor compressor, and the solar assisted TVC. The third is the solution via other techniques. Nowadays, researchers are focusing on development and improvement in the existing meta-heuristic techniques. Also, much work is done on the hyper-heuristics. So this we can also address in the future scope. The next is the impact of NT on the dynamic solution. I have only considered the effect of the number of approximation terms taken as 3, 6, and 9, but further work needs to be done to exactly understand the behavior of the response based on the NT. And the fourth thing is the design of controllers, including the advanced controllers, which are essential to guarantee that there is no noise, that is to ensure disturbance rejection, noise suppression, and to track the variations in set point. So all this future scope work are now being paid attention to right now under the supervision of Dr. Om Prakash Verma, and I am also focusing on this work under his supervision. And these are the list of published, accepted, and communicated papers in journals, in conferences and book chapters. These are the references which I have taken. So thank you. That's all from my side. And I welcome the questions from the external examiner and the faculty members and the students.
Okay, Drishti, very good work. Okay, and a good publication also. Just for my understanding, I want to ask some questions here. Okay, what is the objective of this multi-evaporator?
Sir, this multiple effect evaporator is used for concentrating the black liquor from
Black liquor.
Yes, sir, black liquor. It is a waste residue from the paper mill.
Okay, waste residue from the paper mill. Okay.
Yes,
okay.
sir. Yes.
So, if concentration of that is controlled, then what will be the outcome of that?
Sir, because they have to use the black liquor as a biofuel, and we have to ascertain that the final output should have some specific concentration so that it can be processed as a biofuel. So accordingly, we have to design a good controller which can monitor that the concentration is up to the specific standard.
Okay. This model.
Yes, sir,
Please.
please. Can you give me two or two example where these biofuels are used inside the paper mill or outside the paper mill, Drishti?
Sir, inside the paper mill, we have the Tomlinson recovery boiler. For heating purpose, the biofuel obtained from the black liquor has been utilized. But for transport applications, inside the industry also, for transportation of we can say the slurry and other such residues, the black liquor has been utilized.
In the form of which form? In which form? Black liquor should be converted into the which form? It likes ethanol, no? It may be the
Yes, sir.
ethanol.
Yes.
Sir, usually methanol and hydrogen are used, but ethanol also it is also used.
So how the black liquor may be converted into these forms? Any idea?
Sir, firstly, we have to convert it into a concentrated form, and then the further processing is done. But I don't know what all processes are involved in the conversion of black liquor to biofuel.
That method is by pyrolysis. You just to know what is the pyrolysis, you know? Pyrolysis is the method by which you can convert that. Okay, sir. Please ask some question.
Okay. So, Drishti, you have used a dynamic model or any regress model or semi-regress model? Which model you used?
Sorry, sir. Can you please repeat?
आपने कौन सा मॉडल यूज किया है इस सिस्टम का? जो मल्टीपल इफेक्ट इवेपोरेटर है, आपका डायनेमिक मॉडल है, रिग्रेस मॉडल है, सेमी रिग्रेस मॉडल है, कौन सा मॉडल? Which model?
Sir, dynamic model.
Okay. So there will be this the revaler is available in your model. Okay. Revaler तो होगा ना इस मॉडल में, because evaporator is there.
Yes,
Evaporator itself is a revaler.
Yes, sir.
Okay. So how do you control the flow of vapor
Sir, actually, I have not worked on the controller design part. I have just obtained the solution
So
नहीं,
what is your idea?
मैं
What is your
नहीं नहीं
idea?
dynamic
मैं
logic.
कंट्रोल की
That
बात
is
ही नहीं कर रहा
how
हूँ।
the
जो जो वेपर का फ्लो रेट है, जो
अच्छा
वेपर का फ्लो रेट है, वो कहीं ना कहीं टेम्परेचर पे डिपेंड कर रहा होगा ना। जितना ज्यादा
yes sir
टेम्परेचर होगा इवेपोरेटर का, उतनी ज्यादा फ्लो रेट होगा वेपर का। सिंपल, ये तो सिंपल रीजन है, विदाउट एनी
yes
कंट्रोल।
yes sir yes sir sir means usually as per the operating plan the individual effects of the evaporator are operated at a specific range of temperature.
ओके
Sir, that feasible bound I have taken in the model simulation.
ओके, ठीक है। एक चीज और बताइए आपका,
Yes
दिस क्वालिटी of this
yes sir
product,
yes
concentration
sir
of the product,
yes sir
how to measure this concentration of product? जो
sir
ब्लैक लिकर का
using
आप
the
कंसंट्रेशन की बात कर रहे हैं।
yes sir using the composition controller we can measure that, means we can control and analyze.
So what is
नहीं
the different composition? What is the
नहीं
analyzing?
नहीं, देखो आपका एक चीज है ना, उसमें 100% वो प्योर है,
Hmm.
Yes sir
98% प्योर है। अगर 98% प्योर मींस इट इज 2% इम्प्योरिटी,
Hmm.
दैट्स
yes
व्हाई।
sir
ठीक है, तो वो जो 90% 98% प्योरिटी है, उसको मेजर कैसे करेंगे,
Hmm.
बता सकते हैं? अभी नाउ
no
इन
sir
कोविड, कोविड 19 जनरली आपको पता होगा कि this alcohol should be 60% in the sanitizer, then
Ah,
only
yes.
yes sir
that will be useful for hand sanitization or sanitization of your home or something just like that.
Hmm.
Okay,
yes
so what is the meaning of that 60%, and how to ensure that 60% pure one component is available, this concentration? Okay, चलो,
sir to
इसकी इसकी जो यूनिट क्या है कंसंट्रेशन की?
sir concentration is unitless, means it is on dry solid percentage of dry solid per
नहीं तो
total
ठीक,
solid content.
नहीं जनरली जो ये ना, ये केमिकल इंजीनियरिंग में यूज होता है, यूनिटलेस नहीं है। कंसंट्रेशन इज कम्स आउट टू बी इन परसेंट ऑफ मोल फ्रैक्शंस।
yes sir yes sir
ठीक है, ये जो
hmm.
यूनिट है ये परसेंट ऑफ मोल फ्रैक्शंस में आता है जनरली। ठीक है,
Hmm.
प्रोसेस इंडस्ट्रीज में। ओके, एंड जो इसका जो आपका ये है कंसंट्रेशन, आप सिर्फ सिमुलेशन में तो आप इसमें डायरेक्टली उससे मेजर कर सकते, डायरेक्टली कैलकुलेट कर सकते हैं, लेकिन
Hmm.
एक्चुअल केस में आपको ये रिफ्रैक्टोमीटर से जाना पड़ेगा। देयर आर टू टाइप्स ऑफ रिफ्रैक्टोमीटर, एक तो एनालॉग होता है, एक डिजिटल होता है। तो आज की डेट में काफी एडवांस रिफ्रैक्टोमीटर्स आ रहे हैं, डिजिटल रिफ्रैक्टोमीटर। वो एक सैंपल आप उसमें डालेंगे एंड इट विल टेक 1 or 2 minutes एंड इट विल टेल दैट व्हाट इज द कंसंट्रेशन ऑफ दैट सैंपल बेसिकली। ठीक है, एक तो उससे हो जाता है, उससे सीधे डायरेक्ट मेजर कर सकें। दूसरा एक और है इसका मेथड मेजर करने का, कि जो नॉर्मल आपका ये होता है ना, जो एनालॉग रिफ्रैक्टोमीटर होता है, उसमें माइक्रोस्कोप होता है उसके साथ
yes
रिफ्रैक्टोमीटर।
sir
तो
hmm.
उसके साथ हम सैंपल लेते हैं। सैंपल दे वी यूज्ड टू कीप एज ए स्लाइड इन द माइक्रोस्कोप एंड वी यूज्ड टू हैव द टू लेयर्स इन बिटवीन। तो वहाँ पर एक लेयर थोड़ी डार्क होती है और एक लेयर ब्राइट होती है। तो उन दोनों को बीच में हम उसको सेटल करते हैं, फिर वहाँ पर हम रिफ्रैक्टोमीटर उसका मेजर करते हैं, रिफ्रैक्टिव इंडेक्स मेजर करते हैं उसका। तो रिफ्रैक्टिव इंडेक्स मान लीजिए जैसे 10% आपका प्योरिटी है, प्योर कोई सॉल्यूशन है, 10% प्योरिटी है, 90% इम्प्योरिटी। 10% प्योर मीन्स 90% इज इम्प्योरिटी,
yes
दैट इज द
sir
मीनिंग। ठीक है, तो पहले 10% का आप रिफ्रैक्टिव इंडेक्स ले लीजिए, फिर 20% का ले लीजिए, फिर 30% का ले लीजिए, और उस तरीके से आप एक रिलेशनशिप आप क्रिएट कर सकते हैं, एक टेबल क्रिएट कर सकते हैं इस तरीके से, रिफ्रैक्टिव इंडेक्स वर्सेस कंसंट्रेशन ऑफ दैट पर्टिकुलर कंपोनेंट।
okay
ओके, और बाद में आपका कोई भी सैंपल आता है, आप उस सैंपल का रिफ्रैक्टिव इंडेक्स मेजर करिए और टेबल से आप बता दीजिए कि इसका ये होता है। ठीक है, दिस इज मतलब मैनुअली हम लोग ऐसा ही करते हैं।
okay
Okay,
sir hmm.
this is the
yes
manual
sir
measurement of the concentration. Okay,
yes sir
otherwise for modeling के लिए तो ये होता है। ठीक है, that is it.
yes sir yes
Okay, आपने एक चीज और इसमें कहा है, जैसे फॉर फ्यूचर प्लान, फ्यूचर वर्क।
yes sir
Okay,
yes sir
so have you utilized this the thermal energy of the walls of this evaporator?
no sir I am not working on that actually my
नहीं, जब आप मॉडलिंग पर आते हैं ना, जो एनर्जी इक्वेशंस होती हैं
Senior
थर्मल,
research scholar is working on that one.
ओके ओके ओके, जो थर्मल एनर्जी इक्वेशंस होती है ना
Yes,
इसके,
sir.
तो उस केस में जनरली वी एज्यूम that the valves are not consuming any energy. However, in
Yes,
practice,
sir.
Yes, sir.
they
Yes,
used
sir.
to have
Yes, sir.
some
Yes,
sort
sir.
of energy. ठीक है,
Mhm.
Yes, sir.
and
Yes, sir.
हाँ, और जनरली we used to say that everything is adiabatic, कि हम
Yes,
चारों
sir.
तरफ से उसको एक
Isolation.
इंसुलेशन यूज कर रहे हैं, इंसुलेशन यूज कर रहे हैं, सो दैट देयर इज नो कंजम्पशन ऑफ द एनर्जी. ठीक है,
Yes, sir.
हाँ, वो भी एक चीज होती है उसके साथ.
Mm-hmm. Yes, sir.
So the good work, there is no, okay, everything is fine.
Okay.
Okay,
Thank you, sir.
thank you, thanks.
Doctor sir, Dr. Singla, you do you want to comment any? You want to?
No, I think it's okay. The work done is satisfactory, and I congratulate this candidate, Drishti Yadav, for the good work that has been done.
Thank you, sir.
And best wishing you a best wishes for your future PhD. I think wherever you will be going,
Mhm.
right?
Thank you, sir.
So
Thank
you
you.
do
Thank
one
you.
thing. You now submit the thesis and kindly make sure that in that thesis submission, that plagiarism report, everything is there. Because
Yes,
I
sir.
think
Yes, sir.
one digital Om Prakash, you can see one digital, I think depository is also there, Shad. I think
Yes, sir. Yes, sir. Yes, sir.
you can just see it out before. Because after that only they will be releasing no dues,
So
right?
Drishti is now selected as a PhD in IIT Madras. So I
Okay,
also congratulate.
okay,
Congratulations.
congratulations, Drishti.
Also
Thank you,
congratulate.
sir.
Good, good.
And
Very
one more place he has he got the chance at University of Vienna, Austria.
good. Oh, good.
That
Okay.
that rank is 120 worldwide in QS ranking. So
Mhm.
if all things will going good, then they must join the University of Vienna. So I once
Okay.
again congratulate Drishti for your hard work, and you have done working very hard day night work. So God is paid and proud of you. Thank you.
Thank you, sir.
सर
Thank
तो
you.
लास्ट में अब इसको कुछ करना है हम लोगों को संजय सर बस हमें अब सर्टिफिकेट दे देना है.
नहीं हमें कुछ नहीं करना है. We will
हाँ.
just send a report, and along with that report, that then they will issue the format which is to be submitted containing all those things. Like
Okay.
one will be the soft copy of the thesis, I think, and one will be the no due certificate.
Just
That
we
each
take the
one.
signature. Just we take the signature of Professor Vijender sir.
हाँ
है ना?
वो
I
that
will.
so that format ना
I will.
that format we will be one there is a format of complete marks. Remember
Mhm.
that format in which we used to put the
I will
marks.
take from the office. I will take from the office and send
हाँ,
to the
you take
Vijender sir.
from the office and then we can send to external examiner Dr. Vijender Singh, and then they can sign it out and final result will be declared.
Okay. Okay sir. Okay sir.
Right, I think that will be okay.
Okay.
Okay,
Any
okay,
comment?
डॉक्टर सिंगला जी नमस्कार.
नमस्कार सर,
हाँ,
नमस्कार.
हाँ, क्या हालचाल है? एवरीथिंग इज फाइन.
एवरीथिंग इज फाइन सर, आप बताइए आपके एंड पे.
बस बस एवरीथिंग इज फाइन. गुड.
चलिए सर, बहुत अच्छा सर.
नहीं, बहुत
एक्चुअली
अच्छा.
मैंने बीच में इंटरप्ट नहीं किया, मैंने कहा अब चल रहा है भाई, लेट अस गो ऑन.
नहीं नहीं, गुड गुड, बहुत बढ़िया, बहुत अच्छा.
बहुत बढ़िया सर, बहुत
हाँ,
बढ़िया.
नहीं, वेरी गुड वर्क, वेरी गुड.
राइट सर, राइट सर. अभी तो और भी आएंगे सर.
हाँ, डेफिनेटली, नो प्रॉब्लम, इट्स
ठीक
ओके.
ठीक सर, ठीक.
हम
ओके
यही
सर,
चाहते
ओके.
हैं अच्छे अच्छे बच्चे निकले करके, सब अच्छे
Hmm.
करके निकले.
नहीं सर, अच्छे हैं स्टूडेंट सर, ऐसी बात नहीं है.
बिल्कुल बिल्कुल बिल्कुल.
Hmm.
ठीक
ठीक है, ठीक.
ठीक
ओपी, आई
ठीक.
थिंक यू कैन वाइंड अप द सेशन.
Thank you. Okay.
ठीक.
Okay. Thank you, Professor Vijender and Dr. Singla, for giving the time, precious time to our students. So thank you, Drishti, once again, and I'm
Thank you,
I'm
sir.
closing the session. Okay.
ओके,
Yes, sir.
थैंक यू, थैंक यू.
Okay.
Thank you,
Thank you.
sir.